Greetings, and thank you for joining us on the Sleep Science Top 1. Outside, the world buzzes with activity and noise, yet within these walls, time seems to take a breath. This evening, our focus isn't on the peaks, the flowing waters, or the stars above. We are entering a concealed dimension, where a solitary light quantum moves like a wave, but behaves like a particle, where atoms can interact over great distances, and even the most barren, empty space teems with energy. We will journey softly, navigating quantum fields, teleporting particles, and instances where the act of perception alters reality. Parts of what you hear this evening might leave you feeling perplexed. Some may linger, reminiscent of a dream that eludes clear definition. Before we dive in, if these soothing and inquisitive journeys assist you in relaxing or provide a peaceful conclusion to your day, think about liking and subscribing. Feel free to express your opinions in the comments section below. It assists others in discovering their path here as well, one drowsy spirit at a time. All right, if you're prepared, let's get started. The principles of physics undergo significant transformations at minuscule scales. In our daily lives, physics seems reliable. Apples descend, clocks move forward, light moves in direct paths. However, when you reduce your perspective to the scale of atoms, the well-known principles start to bend. At the quantum scale, particles often do not follow predictable trajectories. They adhere to probabilities, resembling indistinct clouds rather than concrete points. Causes and effects do not align in the tidy, straightforward manner we anticipate. Events may appear to unfold without obvious explanations. At times, two paths emerge simultaneously, awaiting a decisive moment to determine the direction forward. This unusual transition from the expected to the uncertain is what makes quantum physics seem like an alternate reality, concealed within our own. The everyday rules don't actually break. Rather, they were never the complete narrative. Below them rests an unfamiliar, gentler structure that unites all things in manners we are just starting to comprehend. Quantum physics rules over a realm that is entirely different from our everyday experiences. The quantum world is something that most of us will never experience firsthand. Their smallest components are significantly smaller than the wavelength of visible light, rendering them perpetually invisible to us. However, their actions influence every aspect of our existence, from what we touch and breathe to who we ultimately become. In this hidden domain, particles float like waves on water, materializing for brief instances, and occasionally behave as if they occupy multiple locations simultaneously. The principles outlined here are articulated in a mathematical language so peculiar that even experienced physicists frequently acknowledge they apply the equations without asserting a complete understanding of their significance. This is not merely a scaled-down version of our reality. It is an entirely distinct realm, functioning on principles that challenge our conventional understanding. Without this unseen realm subtly unfolding its designs, the observable universe, along with our existence, would not be possible. Energy is not a continuous flow. It exists in small, discrete packets. During the late 1800s, scientists believed that energy was continuous, resembling water streaming from a faucet. Then came the surprise. Under specific circumstances, it's anything but smooth. Light, heat, and various other forms of energy consist of minuscule, indivisible quanta. A quantum represents the tiniest unit of energy that a system can either acquire or relinquish, akin to the smallest denomination in the universe's currency. This finding, ignited by research into the interaction of light and matter, challenged long-standing principles of physics. It clarified the reasons behind the specific colors emitted by heated objects, the process by which atoms absorb and release light in distinct bands, and the phenomenon where energy seems to manifest in distinct jumps rather than continuous flows. Without this concept, referred to as quantization, contemporary advancements such as lasers and computers would not be possible, and the path to quantum theory may have remained unexplored. substance can move in a wave-like manner, but can also hit with the force of a particle. It seems unfeasible. In what way can an entity exhibit characteristics of both a wave and a particle? That is precisely how quantum objects function. Illuminate two narrow slits and observe as it disperses into undulating interference patterns, a signature of wave behavior. However, when you detect the light, it arrives particle by particle, with each one landing at a precise point, resembling a small buoyant object. This holds true for probability wave clouds, atoms, and even certain large molecules. This wave-particle duality indicates that particles do not move like small billiard balls. Instead, they exist as probabilities distributed throughout space until they are observed. Subsequently, their wave-like distribution converges into a specific point. This peculiar dual identity is not merely a curiosity. It lies at the core of quantum mechanics. What we perceive as solid and localized is, in reality, an element of a broader, dynamic pattern that becomes clearer when we focus our attention. Just observing can alter the course of reality. In the realm of quantum mechanics, observation is an active process. Measuring a particle can alter its state. The renowned quantum interference setup reveals that light quantums, or probability wave clouds, create wave-like patterns when unobserved, yet exhibit particle-like behavior when their paths are monitored. It seems that nature is aware of our observation, although physicists attribute this phenomenon to the inevitable interaction between the measuring instrument and the system itself. This still brings up significant inquiries. If every measurement influences reality, then what does reality consist of prior to the measurement? Is the world caught in a vague limbo until an external force compels it to make a decision? The concept that observation alters the outcome, whether viewed as a physical phenomenon or a philosophical enigma, stands as one of the most perplexing realities of quantum mechanics, captivating and disturbing scientists for more than 100 years. Nature prevents us from having complete knowledge about a particle. Classical physics assured that with precise measurements, one could attain complete knowledge of a system, including its position, speed, and future trajectory. Quantum mechanics presents a different perspective. The Heisenberg uncertainty principle indicates that there are constraints on our ability to know certain things simultaneously. For instance, the greater your accuracy in determining a particle's position, the less accurate your understanding of its momentum will be, and the opposite holds true as well. This is not a defect in our instruments. It is an inherent aspect of nature. Particles do not possess precise values for specific pairs of properties simultaneously. The uncertainty is genuine and inescapable. This indicates that, at the quantum level, it is impossible to predict the future with complete precision. Our focus is on calculating probabilities, a change in perspective that revolutionized science and questioned our fundamental beliefs about determinism. A particle can be in multiple states simultaneously. Superposition stands out as one of the most peculiar ideas in quantum physics. The concept that a particle may simultaneously occupy various states or positions. And probability wave cloud has the ability to spin both up and down at the same time, while a light quantum can travel along multiple paths simultaneously. These states are maintained in a fragile equilibrium, as outlined by a mathematical wave function. It is only upon making a measurement that the particle selects a specific outcome, causing the superposition to disappear. This goes beyond mere theory. Repeated experiments consistently validate this finding. Quantum computers utilize superposition to execute numerous calculations simultaneously, providing them with significant potential power. In our daily experiences, superposition cannot be observed directly, as it ceases to exist the moment we engage with it. However, at the quantum level, this is the standard. Remember that our daily existence is merely one interpretation drawn from a vast array of potential realities. Reality is constructed from probabilities rather than certainties. Within the subatomic realm, certainty is elusive until an event unfolds. The position, momentum, or spin of a particle is not predetermined in advance. A set of probabilities describes it. The probabilities are represented in the particle's wave function, which progresses steadily until an interaction or measurement takes place. At that point, a single outcome appears, seemingly selected at random from the array of possibilities. This inherent probabilistic nature is not a result of ignorance. Rather, it is a fundamental aspect of how the universe operates. Even with complete understanding of the wave function, you can only forecast probabilities, never certainties. This caused discomfort among numerous physicists, including Einstein, who famously remarked that God does not play dice with the universe. However, more than 100 years of experiments have demonstrated that, at the tiniest scales, probability does not indicate a lack of complete understanding. It is the essence of reality. The way in which possibilities transform into reality remains an enigma. A quantum system can exist in multiple states simultaneously, and measurement plays a role in narrowing these possibilities down to one definitive outcome. However, the precise mechanism behind this collapse, or whether it truly exists, continues to be one of the most significant enigmas in the field of physics. Certain interpretations indicate that collapse is a physical phenomenon initiated by observation. Some assert that every possibility occurs, yet we only perceive a single branch within a broader multiverse. One perspective suggests that collapse is merely an illusion, and the wave function never actually reduces at any point. After many years of discussion, there remains no agreement. This moment, where we transition from numerous possibilities to a singular outcome, is fundamental to our understanding of reality. Grasping it might necessitate not only fresh physics, but also a more profound understanding of consciousness and the boundaries of knowledge. Quantum cat paradox exists in a state of being both alive and dead until an observation is made. In 1935, physicist Erwin Schrödinger introduced a thought experiment to illustrate the peculiar nature of quantum superposition as it relates to familiar objects. Picture a cat enclosed in a sealed box, alongside a mechanism that operates on a 50-50 probability of releasing poison, contingent upon the decay of a solitary atom. According to quantum theory, an atom exists in a state of superposition, being both decayed and not decayed until it is observed. Therefore, theoretically, the cat can be considered both alive and dead simultaneously. The superposition collapses into a single outcome only upon opening the box. Schrödinger's intention was not to suggest that we should interpret this literally for cats. Rather, he aimed to emphasize the absurdity of applying quantum rules to the macroscopic world. Nevertheless, his renowned cat continues to be one of the most vivid and lasting representations of the peculiarities of quantum mechanics. Two particles can coexist in the same space. Entanglement stands out as one of the most perplexing aspects of quantum mechanics, a phenomenon in which two particles become so intricately connected that their states can no longer be considered independent. When you measure one, the properties of the other align immediately, regardless of the distance between them. It seems that they are not merely two particles, but rather a single system extended throughout space. This bond remains strong, regardless of the distance, and it doesn't depend on conventional signals moving between them. Once intertwined, the particles possess a shared identity of sorts. Researchers have successfully generated entanglement in laboratory settings using light quantums, probability wave clouds, and even small clusters of atoms. The connection is delicate, susceptible to disruption from external factors, but when maintained, it suggests a profound dimension of existence, where division is merely a facade and the cosmos is far more intertwined than our perception allows. Touch one particle here, and another reacts immediately from a distance. When you take two quantum non-local twins and position them at opposite ends of the Earth, an extraordinary phenomenon occurs. Measuring one immediately reveals the condition of the other. This occurs even when they are so distant that light, the quickest entity in the universe, wouldn't be able to transmit a message between them promptly. Information does not travel faster than light. The two particles, in fact, do not possess independent states from the outset. In a way, they are identical. This immediate link has undergone rigorous testing in laboratories, with ranges extending from meters to hundreds of kilometers. The outcomes consistently align with the predictions of quantum theory, regardless of how perplexing they may appear. This serves as a reminder that our common understandings of cause, effect, and distance might not hold true in the fundamental mechanisms of nature. Even Einstein found this quantum connection unsettling. Albert Einstein was well known for his aversion to the concept of entanglement. He referred to it as eerie interaction across space, firmly believing that it could only be a partial account of existence. He believed that there must be concealed variables, invisible elements that could account for the peculiar relationships between particles without resorting to faster-than-light phenomena. In 1935, he, together with Boris Podolsky and Nathan Rosen, introduced a thought experiment that has come to be known as the EPR paradox, aimed at questioning the principles of quantum mechanics. They contended that if quantum theory held true, it suggested either unfeasible communication between far-off particles, or that the particles lacked definite properties until observed, both of which seemed ludicrous. Years later, experiments demonstrated that entanglement is indeed real and cannot be solely accounted for by hidden variables. Interestingly, Einstein's own challenge played a pivotal role in inspiring the research that validated the most enigmatic aspect of quantum mechanics. Research indicates that this bond is genuine and enduring. For many years, entanglement was a conundrum confined to theory. Beginning in the 1970 seconds, physicists initiated the design of experiments aimed at directly testing it. By utilizing pairs of light quantums, they assessed the correlations between them and contrasted the findings with the forecasts of quantum mechanics against those of classical hidden variable theories. The outcomes were clear-cut. Quantum mechanics has triumphed. Since that time, the tests have become increasingly accurate, eliminating gaps and increasing the distances between quantum non-local twins. In 2017, researchers transmitted entangled light quantums between terrestrial stations and an orbiting satellite, validating the phenomenon over distances exceeding 1,000 kilometers. Every success reinforces the idea that entanglement is not merely a laboratory oddity. It is an essential aspect of reality. It may seem odd, but the universe permits this flawless connection to thrive without any apparent link whatsoever. There is no concealed mechanism that accounts for these unusual correlations. Einstein envisioned that entanglement might be clarified through hidden variables, concealed information possessed by particles that dictates their behavior in advance. In the 1960 seconds, physicist John Bell developed a mathematical test to determine the existence of such variables. His result, referred to as Bell's theorem, demonstrated that if hidden variables existed, the correlations between quantum non-local twins would be constrained in particular manners. Quantum mechanics forecasted more robust correlations, and experimental results consistently confirmed this observation. This indicates that any theory, based exclusively on concealed local information, cannot completely account for the events occurring. The essence of the universe does not conform to the neat, predictable laws that Einstein imagined. Rather, it acts in a manner that implies reality is more intricately linked and possibly less localized than we had previously thought. Bell's theorem demonstrated that the universe does not operate according to classical principles. Bell's theorem stands as a remarkable achievement in the field of physics. It goes beyond merely stating that quantum mechanics is strange. If the theory holds true, it indicates that the universe cannot be understood through any classical model that depends on local causes. The alignment of experiments with quantum predictions suggests that nature either permits instantaneous influences over distances, or it relinquishes the notion that objects possess definite properties prior to measurement. Regardless, it compels us to reconsider the nature of reality and the framework that underpins it. Bell's work, which was once considered a niche topic, has now taken center stage in quantum information science. It has established the foundation for technologies such as quantum cryptography and secure communication, all rooted in the eerie phenomena that Einstein questioned. Quantum teleportation transfers the identity of a particle to a different location. Quantum teleportation is not a concept from science fiction. It does not transport objects across space instantaneously. Rather, it conveys the state of one particle to another, utilizing entanglement as the connection. Initially, two particles become entangled. One goes to the destination, while the other remains with the sender. Through a unique joint measurement conducted on the sender's particle alongside the particle designated for teleportation, the quantum state is annihilated in one location and re-established in another. No physical substance moves, but the precise quantum information is transmitted. This method has been shown to work with light quantums, atoms, and ions across distances that vary from several meters to hundreds of kilometers. It's an essential component for constructing quantum networks, and while it may not transport humans through space, it performs something just as remarkable. A quantum system's identity can jump from one place to another. There are those who believe that space-time arises from entanglement. Recently, an intriguing concept has emerged, suggesting that the fundamental structure of space-time could be intricately linked to quantum entanglement. This perspective suggests that the geometry of space, including distances, curves, and the connections between points, may represent the large-scale manifestation of innumerable microscopic quantum links. If this is accurate, it suggests that gravity and the universe's shape are not intrinsic properties, but rather arise from a more profound layer of quantum information. Theoretical investigations in fields such as holographic duality and tensor networks suggested potential mechanisms for how this connection could function. This concept, though still in the realm of speculation, has the potential to bring together general relativity and quantum mechanics into one cohesive framework, suggesting that the very fabric of space could come apart in the absence of entanglement. The cosmos could be intricately interconnected through quantum connections. If entanglement is as widespread as quantum theory implies, then it transcends mere laboratory curiosity. It is occurring constantly in every corner of the universe. Particles generated in far-off stars, ancient cosmic occurrences, or even the Big Bang itself, might still be linked by unseen connections. In this regard, the universe resembles not a collection of distinct entities, but rather a unified, cohesive entirety. While these connections might diminish when disrupted, new ones are continuously created as particles engage with one another. This concept of reality being intricately woven together contests the notion of the cosmos as a boundless void, scattered with solitary fragments of matter. Rather, all things could be components of a continuous quantum dialogue, articulated in the common dialect of entanglement. Quantum non-local twins can maintain their connection despite any challenges. Entanglement is fragile. It is susceptible to destruction from heat, noise, or environmental interactions. However, under certain circumstances, it can endure in unexpected manners. Some systems, such as superconductors and Bose-Einstein condensates, are capable of maintaining large quantities of particles in entangled states that persist over extended durations. In the chaotic and loud environment beyond the lab, evidence of entanglement has been detected among particles that are far apart from each other. This resilience transforms entanglement from a mere fragile curiosity into a valuable asset for practical technologies. By mastering the art of protection and control, we can leverage these lasting connections to drive advancements in quantum communication, computing, and sensing, fundamentally changing our methods of sharing and processing information. Probability wave clouds are incredibly tiny, yet they disperse like clouds. And probability wave cloud is among the most recognized subatomic particles. It travels along wires, connects atoms, and influences the essence of life itself. However, when researchers attempt to gauge its dimensions, they encounter something perplexing. It acts as though it lacks any internal structure and does not possess a measurable diameter. Simultaneously, it does not function as a precise marker. Rather, its existence is dispersed in a probability cloud encircling the atomic nucleus, with formations dictated by quantum principles. The probability wave cloud should not be thought of as a tangible mist. Rather, it serves as a representation of the probable locations of the probability wave cloud. At one moment, it could be close to the nucleus, and in the next, it might be far away. It's impossible to determine its exact location until you observe it. The dual nature of quantum objects, being both point-like and spread out, serves as a striking illustration of how they challenge our everyday understanding. Even though light quantums have no weight, they are capable of exerting force on objects. Light quantums, which are the fundamental particles of light, possess no mass. However, they do carry both energy and momentum. This indicates that they can apply force upon impact with an object, a phenomenon referred to as radiation pressure. In the vastness of space, devoid of air to hinder motion, even the smallest nudge can lead to significant changes as time progresses. Sunlight has the ability to gradually change the trajectories of dust, grains, asteroids, and spacecraft. Engineers have created solar sails, large reflective sheets that harness sunlight's momentum for propulsion, eliminating the need for any fuel. On smaller scales, focused beams of light can capture and manipulate microscopic objects, a method known as optical tweezers, which finds applications in biology and nanotechnology. One of the most surprising and useful quantum gifts of light is its ability to physically move matter despite having no rest mass. Every second, billions of ghostly ghost particles flow through you. In every instant, without your awareness, an endless flow of ghost particles passes through you. These almost weightless particles are produced in vast quantities by the sun, far-off stars, explosive supernovae, and even through radioactive decay occurring in the Earth's crust. Ghost particles have such a minimal interaction with matter that they can traverse entire planets as though they were moving through an empty space. Trillions of them are coursing through Earth, and you at any moment, yet identifying them proves to be remarkably challenging. Massive subterranean detectors, brimming with ultra-pure liquids or ice, stand ready for the infrequent occurrence when a neutrino interacts with an atom. Examining them can uncover insights into the functioning of stars, the evolution of the universe, and the potential symmetry between matter and antimatter. Ghost particles, elusive and nearly undetectable, serve as evidence that the universe is teeming with concealed activity and energy that often goes unnoticed. Fundamental quarks are always found in pairs or triplets. Fundamental quarks serve as the essential components of protons and neutrons, which constitute the majority of the matter we observe. However, in contrast to probability wave clouds, fundamental quarks are never observed in isolation. The strong nuclear force confines them, with mediation occurring through particles known as strong force carriers. The force intensifies as fundamental quarks are separated, similar to the increasing resistance felt when stretching a rubber band. When you attempt to separate fundamental quarks, the energy you introduce will ultimately lead to the formation of new quark pairs, which promptly combine to form new particles. This phenomenon, referred to as confinement, indicates that fundamental quarks remain permanently bound in pairs of mesons or triplets of baryons. It seems that nature has determined that fundamental quarks are destined to never journey alone. They are present solely as components of a larger entity, intertwined within the core of each atom's nucleus. Strong force carriers create the most powerful connections in the universe. The strong nuclear force stands as the most formidable among nature's 4 fundamental forces, with strong force carriers serving as its carriers. Their name is derived from their function, which involves binding fundamental quarks to create protons, neutrons, and various other particles. However, strong force carriers differ from the force-carrying particles found in electromagnetism or gravity. They engage not just with fundamental quarks, but also with one another, forming a compact, self-sustaining network that confines fundamental quarks within. The intensity of the strong force is such that separating a single proton demands energies that far exceed what we can generate on Earth. Except in the context of particle accelerators, atoms and the matter they constitute would not be able to exist without strong force carriers. Strong force carriers serve as the unseen connections that bind the universe at its most fundamental levels. The absence of the Higgs particle means that mass would not be present. The Higgs particle, found in 2012 at the CERN Large Hadron Collider, completed the standard model of particle physics. It is linked to the Higgs field, an unseen energy field that fills the entirety of space. When particles traverse this field, they engage with it, and this engagement imparts mass to them. If there were no Higgs field, particles such as fundamental quarks and probability wave clouds would lack mass, preventing the formation of atoms, planets, and ultimately, life itself. The Higgs particle is essentially a quantum fluctuation within the Higgs field, observable solely during high-energy collisions. The discovery validated a long-standing theory and awarded Francois Englert and Peter Higgs the Nobel Prize. It offered a deep response to a straightforward inquiry. What is the reason behind the weight of objects? Empty space teems with ephemeral empty space fluctuations. Even in a perfect empty space, space is not genuinely devoid of substance. According to quantum field theory, pairs of particles and antiparticles continuously emerge, momentarily borrowing energy from the empty space, only to annihilate and vanish shortly thereafter. While these empty space fluctuations remain unobservable directly, their impacts can indeed be quantified. For instance, they induce minute changes in the energy levels of probability wave clouds within atoms and generate forces between objects in a Prosser, empty space, referred to as the Casimir effect. This ongoing flurry of movement suggests that empty space resembles a turbulent sea, rather than a calm emptiness. The notion that nothing is actually teeming with temporary, unseen particles stands as one of the most peculiar and well-supported predictions in the realm of quantum physics. The quantum empty space is teeming with energy. All those transient empty space fluctuations in the empty space possess energy known as zero-point energy, which remains present even when a system reaches its minimum energy state. In theory, each cubic centimeter of vacant space holds a vast quantity of this energy. Much of it neutralizes or stays out of reach. Yet its influences can still be observed in nuanced manners, like in atomic behavior and the universe's expansion. In the field of cosmology, there are scientists who propose that dark energy, the enigmatic force responsible for the acceleration of the universe, could be associated with empty space energy. The contradiction lies in the fact that theoretical calculations indicate an empty space energy that is significantly greater than our observations, implying that our grasp of one of reality's most essential components remains incomplete. Antimatter is the flawless counterpart to matter, yet entirely its opposite. Each type of particle has a corresponding antiparticle that shares the same mass but possesses opposite charge and differing properties. Upon encountering its antiparticle, a particle undergoes annihilation, resulting in a release of pure energy. In 1928, Paul Dirac made a groundbreaking prediction about antimatter, which was subsequently discovered in cosmic rays shortly thereafter. It is uncommon in the universe at this time. Much was obliterated in reciprocal destruction soon after the Big Bang. The reason matter persisted while antimatter largely disappeared is one of the significant unresolved enigmas in the field of physics. Antimatter can be produced in particle accelerators, and we are capable of trapping small quantities as well. However, storing it presents difficulties as it disintegrates upon contact with matter. Antimatter is more than merely a curiosity. It holds potential uses in the medical field, including PET scans, as well as in future propulsion systems that might, theoretically, utilize its remarkable energy density. Substance can emerge from sheer energy and be eliminated once again. Einstein's renowned equation, E equals mc squared, reveals that mass and energy represent two manifestations of a singular entity. Given the appropriate circumstances, energy has the ability to convert into matter, and matter can revert to energy. High-energy collisions, such as those occurring in particle accelerators or in the vicinity of black hole horizons, can generate particle-antiparticle pairs from pure energy. On the other hand, when particles encounter their antiparticles, they undergo annihilation, resulting in the creation of light quantums. The ongoing exchange between mass and energy unfolds across the universe, within the cores of stars, during the infancy of the cosmos, and in remarkable astrophysical phenomena. It demonstrates that matter is not a fixed, solid entity. It represents a state of energy, momentarily molded into particles before reverting to light. Each particle represents merely a disturbance in an unseen field. Quantum field theory suggests that the universe is not composed of particles adrift in a void. It consists of foundational areas that extend in all directions. Every kind of particle represents a specific, localized vibration, or ripple, within its respective field. Probability wave clouds represent disturbances in the probability wave cloud field, while light quantums signify disturbances in the electromagnetic field, and similarly for other particles. Even in the absence of particles, the fields continue to exist, permeating all of space. This perspective brings together matter and energy, presenting them as distinct manifestations of the same fundamental essence. It also indicates that particles are not small, indivisible spheres. They are occurrences, disruptions in something more profound and essential. No matter your location, these unseen fields are present, subtly influencing all that you perceive, interact with, and undergo. Quantum field theory combines particles and forces into a unified framework. Prior to the advent of quantum field theory, particles and forces were regarded as distinct entities, separate objects that engaged with one another through unseen influences. However, QFT demonstrated that forces originate from fields, with their effects transmitted by particles. In electromagnetism, the electromagnetic field generates light quantums that facilitate the interaction between charged particles. The strong nuclear force arises from the gluon field, while the weak nuclear force is derived from the W and Z boson fields. It is possible that even gravity could eventually be explained in this manner, although a comprehensive quantum theory of gravity remains out of reach for now. Quantum field theory stands as one of the most accomplished frameworks in the realm of science, with its predictions validated to remarkable accuracy. This represents our most accurate portrayal of reality, at the tiniest scales, serving as a unified language for both the matter that exists and the forces that drive it. Even the most barren space is bustling with energy. While you might picture the empty space of space as a frigid, barren void, quantum physics challenges that notion. Even in the absence of particles, fields are never completely at rest. They tremble with ongoing variations, creating fleeting manifestations of empty space, fluctuations that disappear as swiftly as they emerge. This ever-present background exists in all places, among the stars, within atoms, and even in the emptiness of your living room. It's a force that remains constant, and while much of it is concealed, it leaves detectable traces in experiments. The reality that nothing serves as a dynamic, vibrant medium alters our perception of space. The stage is not merely a backdrop for reality. It plays an integral role, subtly influencing the unfolding drama at every turn. A flawless, empty space has the ability to draw objects toward one another. It resembles something out of a science fiction story. When two uncharged metal plates are positioned closely in an empty space, they will gradually move toward one another. The Casimir effect arises as a direct result of quantum empty space fluctuations. The gap between the plates permits only specific wavelengths of empty space fluctuations to exist, whereas the area beyond accommodates a broader range. The variation in pressure drives the plates to move inward. The effect is remarkably minor, yet it has been observed in laboratories, confirming that the empty space is far from empty. The Casimir effect, while lacking practical application at this moment, serves as a remarkable illustration of how quantum forces can arise from what we perceive as emptiness, influencing the movement of tangible, physical entities. Everywhere in the universe, zero-point energy is present. Even when a system reaches its absolute lowest energy state, devoid of heat, motion, or light, it retains a residual energy known as zero-point energy. This directly stems from the uncertainty principle. A field cannot exist with zero energy, as that would imply having precise knowledge of both its position and momentum simultaneously. Zero-point energy is minuscule when considered on human scales, yet its omnipresence suggests it could accumulate into something vast throughout the universe. Certain theories propose a connection to the enigmatic dark energy that propels the universe's rapid expansion. Regardless of its validity, zero-point energy serves as a prime illustration of the concept that quantum physics presents. Empty space is never genuinely devoid of activity. Empty space can distort gravitational forces and the passage of time. In Einstein's theory of general relativity, mass and energy influence the curvature of space-time, while this curvature dictates the movement of matter. Should the empty space be saturated with quantum energy, it follows that even voids in space possess the ability to influence the universe's geometry. This suggests that quantum effects could have a subtle impact on gravity, and possibly even on time itself. In theory, the density of empty space energy might influence the expansion of the universe, the formation of galaxies, and potentially the flow of time under extreme conditions. The precise nature of this interaction continues to elude understanding, in part due to the challenge of merging quantum theory and gravity into a unified framework, which stands as one of the most difficult issues in physics. However, it may be that the essence of grasping cosmic evolution is concealed within the framework of void space. Strong fields have the ability to alter the characteristics of the empty space. The empty space may seem constant, yet in extreme circumstances, it has the potential to change. Intense electric or magnetic fields have the ability to polarize the empty space, causing its empty space fluctuations to align in manners that modify its characteristics. In theory, if the fields are sufficiently intense, they might lead to a breakdown of the empty space, resulting in the creation of actual particle-antiparticle pairs from the energy. This occurrence, known as empty space decay, has not been directly observed. The necessary fields exceed our current generation capabilities, yet their effects are anticipated by quantum electrodynamics. This behavior indicates that the empty space is not merely a passive backdrop. Rather, it serves as an active dynamic medium, capable of responding to its surroundings in unexpected manners. Black hole horizons emit a glow by extracting energy from the empty space of space. Black hole horizons are well known for their ability to trap everything, including light, within their grasp. Quantum theory suggests that they can gradually emit energy, a phenomenon known as black hole horizon evaporation. Close to the event horizon, empty space fluctuations are in a constant state of generating pairs of empty space fluctuations. Typically, these particles annihilate rapidly, but at the boundary of a black hole horizon, one particle may enter, while the other manages to escape. From an external perspective, it appears that the black hole horizon is radiating energy, gradually diminishing in mass as time progresses. This process is remarkably subtle for large black hole horizons, yet it offers a significant understanding. Quantum physics indicates that even the most enigmatic and seemingly inescapable objects in the universe are not entirely devoid of light. The force of emptiness could be causing the universe to expand. In 1998, astronomers found that the universe is expanding at an accelerating rate. The cause remains a mystery. Yet one prominent possibility is dark energy, a type of energy that appears to be inherent to the fabric of space itself. If dark energy exists, it functions similarly to empty space energy, applying a steady outward force. Over billions of years, this force might extend the universe to such an extent that far-off galaxies drift permanently out of our grasp. The notion that the final destiny of the universe could hinge on the energy of vacuity stands as one of the most unsettling conclusions drawn from contemporary physics. The actual essence of the quantum empty space is still a mystery. The quantum empty space can be mathematically described, its effects measured in experiments, and it can even be linked to phenomena on a cosmic scale. However, we remain uncertain about its true nature. Could it be a tangible substance, akin to an unseen ocean permeating the cosmos? Do fields possess a characteristic that allows them to exist independently of the presence of particles? Or could it be something even more peculiar, possibly linked to the very beginnings of the universe? The empty space occupies a crucial position at the crossroads of quantum theory, relativity, and cosmology, which are three foundational aspects of physics that continue to elude complete unification. Until we grasp it fully, the void between the stars will continue to be one of the most significant and enigmatic elements of existence. Quantum computers have the ability to process multiple realities simultaneously. In contrast to classical computers that handle information using binary bits, represented as either 0 or 1, quantum computers utilize qubits, which are units capable of existing in superpositions of both 0 and 1 simultaneously. This enables them to investigate various potential solutions at the same time, as though they are evaluating results across different scenarios before arriving at a conclusion. This method's effectiveness increases dramatically as the number of qubits rises, allowing some challenges that would require classical computers thousands of years to resolve to be addressed in mere seconds. Quantum computers are currently in their early stages, facing challenges related to error, correction, and stability. Yet, even at this moment, they suggest a future in which challenges in chemistry, cryptography, and optimization might be solved with astonishing rapidity. It's not sorcery. The principles of quantum probability and interference are utilized in a manner that classical logic simply cannot replicate. Qubits have the ability to hold several answers simultaneously. A qubit remains in a superposition of states until it undergoes measurement. Prior to that, it can encompass a mixture of potentials, both null and one, influenced by likelihoods. This characteristic is what endows quantum computers with their immense potential power. With only a few qubits, you can encapsulate an immense array of potential combinations simultaneously. As a quantum algorithm executes, it skillfully adjusts these probabilities in a precise manner, ensuring that the incorrect answers negate one another, while the correct answer stands out. It's akin to exploring a whole library simultaneously, rather than one book at a time. One important aspect to consider is that measurement collapses a qubit state, making it a significant challenge in quantum computing to design algorithms that can effectively extract useful results from this fragile superposition. Entanglement enhances quantum processing significantly. Entanglement is more than just an intriguing phenomenon. It serves as a valuable resource. In quantum computing, entangled qubits exhibit correlations that classical bits cannot replicate, enabling actions on one qubit to immediately affect its entangled counterparts. This allows quantum computers to execute intricate calculations with greater efficiency, connecting far-flung aspects of a problem without the need to transfer physical information. Entanglement contributes to error correction by aiding in the detection and rectification of errors without the need to directly observe the delicate states of the qubit. In the absence of entanglement, quantum computers would forfeit a significant portion of their superiority compared to classical machines. It serves as the unseen connection that unifies their reasoning, empowering them to address challenges that exceed the capabilities of even the most advanced supercomputers available today. Some quantum algorithms have the potential to resolve issues in an instant. Certain quantum algorithms possess such remarkable efficiency that they could, theoretically, solve problems that would confound classical computers for centuries. A notable instance is Shor's algorithm, which can factor large numbers at an exponentially faster rate than the most effective classical techniques, representing a significant advancement that could jeopardize numerous current encryption systems. Another example is Grover's algorithm, which enhances database searches in a manner that no classical method can replicate. While these algorithms do not render quantum computers universally quicker, they can provide a significant advantage for the specific problems they are designed to tackle. Governments, tech companies, and researchers are in a competitive rush to create functional quantum processors. The initial entity to achieve this will unveil computational abilities that have the potential to transform technology and enhance security. Quantum cryptography establishes secrets that remain unbreakable. Classical cryptography is based on the complexity of specific mathematical challenges. However, theoretically, a sufficiently advanced computer could overcome these obstacles. In contrast, quantum cryptography employs the principles of physics to ensure security. The well-known technique, quantum key distribution, QKD, transmits encryption keys that are encoded in the states of light quantums. Any effort to eavesdrop will inevitably disrupt these states, immediately exposing the intrusion. This indicates that it is feasible to achieve secure communication, even through channels that an attacker can completely monitor. Quantum cryptography has been successfully tested in actual networks, such as satellite links, and has the potential to safeguard financial transactions, government communications, and personal data with a high degree of security. Unmatched security that surpasses any traditional system. Quantum sensors pick up the faintest hints of alteration. Quantum sensors leverage quantum effects, including superposition and entanglement, to achieve remarkable precision in measuring quantities like time, acceleration, and magnetic fields. They possess such sensitivity that they can identify changes that are imperceptible to any traditional instrument. Changes brought about by minute gravitational fluctuations, delicate neural processes, or the mere existence of dark matter particles. Certain designs utilize clouds of ultra-cold atoms or nitrogen vacancy centers in diamond to attain this level of sensitivity. Quantum sensors have the potential to transform navigation, medical imaging, and geological surveying in the future, providing unprecedented insights into the human body and the Earth. Superconductors enable electricity to flow indefinitely, without any loss. Typically, electric currents encounter resistance, which transforms a portion of their energy into heat. However, in specific materials that are cooled to very low temperatures, resistance decreases to zero, a phenomenon known as superconductivity. In this condition, probability wave clouds come together and move seamlessly, retaining their energy indefinitely. This phenomenon is fundamentally quantum, depending on the collective behavior of numerous particles functioning as one coherent wave. Superconductors find applications in MRI machines, particle accelerators, and magnetic levitation trains. Achieving superconductivity at room temperature would transform energy transmission, removing waste, and paving the way for innovative technologies. Quantum networks have the potential to link computers worldwide. Just as classical computers connect through the internet, future quantum computers may be interconnected via quantum networks. These networks would leverage entanglement and quantum teleportation to convey information in a manner that cannot be intercepted without being detected. Establishing this network involves the creation and preservation of entanglement across extensive distances, a challenge that researchers are currently exploring through the use of optical fibers, satellites, and quantum repeaters. A fully operational quantum internet has the potential to facilitate highly secure communications, enable distributed quantum computing, and introduce innovative sensing methods that can operate over long distances, effectively transforming the entire globe into one cohesive quantum network. Atomic clocks maintain such precise timekeeping that they experience minimal drift over billions of years. Atomic clocks are recognized as the most precise timekeeping devices globally, utilizing the inherent vibrations of atoms, typically cesium or ytterbium, to measure time. In more sophisticated iterations, atoms are cooled to temperatures approaching absolute zero and stabilized by lasers, enabling their oscillations to be measured with remarkable accuracy. The most accurate atomic clocks would deviate by less than a second throughout the entire lifespan of the universe. This level of precision is not merely theoretical. It is essential for GPS navigation, telecommunications, and scientific experiments. Recent developments in quantum technology are enhancing this precision even more, potentially allowing atomic clocks to sense variations in the flow of time due to minute differences in gravitational potential. Quantum technology is currently transforming the landscape of science. Although quantum computers frequently make the news, quantum technology is actively being utilized in various fields of research and industry. Quantum sensors are charting subterranean formations. Quantum communication links are safeguarding experimental networks. And quantum simulators are assisting researchers in modeling intricate molecules and materials. These tools are not mere fantasies. They represent real-world applications of quantum mechanics that are enhancing our abilities in the present moment. As technology develops, it is expected to impact areas such as climate modeling and drug discovery, providing us with innovative methods to comprehend and influence our environment. The quantum revolution is not a distant future event. It has arrived, subtly transforming our approach to understanding reality. The Copenhagen interpretation posits that reality remains unmanifested until it is observed. The Copenhagen interpretation, formulated in the 1920 seconds by Niels Bohr and Werner Heisenberg, continues to be one of the most commonly taught frameworks for understanding quantum mechanics. A quantum system is proposed to lack definite properties until measurement occurs. Prior to that moment, it resides in a state of superposition, a mixture of every potential outcome. Measurement compels the system to adopt a definitive state, resulting in the collapse of the wave function. This perspective is pragmatic, aligning seamlessly with experimental findings. Yet it raises philosophical concerns. Is reality genuinely reliant on observation for it to take on a specific form? Could it be that the collapse is merely a mathematical convenience we rely on due to our inability to monitor every quantum detail? The Copenhagen interpretation embraces these questions, viewing uncertainty as an essential aspect of the universe rather than a problem to be resolved. The many worlds view suggests every outcome actually happens. Introduced by Hugh Everett in 1957, the many worlds interpretation completely avoids the issue of wave function collapse. It states that when a quantum event presents several possible outcomes, each of those outcomes takes place, but in distinct, branching universes. If a particle could go left or right, the universe splits, creating one version where it goes left and another where it goes right. In this view, reality is an ever-growing tree of possibilities, with countless versions of ourselves living out different histories. While this neatly preserves the equations of quantum mechanics without mysterious collapse, it raises staggering questions. If all outcomes happen, what does it mean to make a choice? And could these parallel worlds ever interact or be observed? Pilot wave theory gives particles hidden paths to follow. Pilot wave theory, also called Bohmian mechanics, offers a more deterministic picture of the quantum world. It proposes that particles always have definite positions and velocities, guided by AEP pilot wave that evolves according to the Schrödinger equation. The strange wave-like interference patterns we see in experiments arise not because particles are smeared out in space, but because this guiding wave influences their trajectories. Pilot wave theory reproduces all the predictions of standard quantum mechanics, but adds hidden variables, unseen details that determine exactly how each particle moves. It's an appealing idea for those uncomfortable with randomness, though it requires accepting non-local effects, where distant events can influence each other instantly. Collapse theories say quantum states can end themselves. Collapse theories propose that superpositions don't last forever. Even without measurement, they eventually decay into a single outcome. In these models, quantum states evolve normally for a time, but have a small chance per unit time to collapse spontaneously. For small systems like atoms, this chance is tiny, allowing superpositions to persist. For larger systems, the collapse happens so quickly that we never notice superpositions in our everyday world. These theories aim to explain why we don't see quantum strangeness at human scales without invoking conscious observers or parallel universes. Experiments are underway to test collapse models by looking for faint, random energy releases that would signal a spontaneous reduction of the wave function. Decoherence explains why quantum strangeness disappears in big objects. Decoherence isn't a separate interpretation, but a physical process that helps explain why quantum effects fade in large systems. Where the quantum system interacts with its environment, air molecules, light, vibrations, information about its state leaks away into countless surrounding particles. This effectively measures the system, destroying the delicate interference patterns of superposition and making it behave more classically. Decoherence happens incredibly fast for macroscopic objects, which is why we never see them in visibly mixed states. While decoherence explains the transition from quantum to classical behavior, it doesn't solve the measurement problem. It still leaves open the question of how one outcome is chosen from the possible ones. The measurement problem still puzzles physicists. At the heart of quantum mechanics lies the measurement problem. How and why does a superposition become a single outcome when observed? The equations describe the evolution of a wave function smoothly over time, but say nothing about the sudden collapse into a definite state. Is this collapse a real physical process, or just an apparent change in our knowledge? Interpretations, from Copenhagen to many worlds to collapse, theories each offer different answers, but none have been proven. The measurement problem is more than an abstract puzzle. It touches on the nature of reality itself, and on whether the world exists in a definite state when no one is looking. Could human awareness decide reality's fate? Some interpretations, often considered controversial, suggest that consciousness itself plays a role in collapsing the wave function. In this view, it's not just physical interaction with a measuring device that determines an outcome, but the awareness of an observer. This observer effect is sometimes overstated in popular culture, but the underlying idea has roots in discussions by physicists like John von Neumann and Eugene Wigner. While most scientists today favor purely physical explanations, the possibility that the mind could influence fundamental physical processes is tantalizing. Testing it is difficult, but the question lingers. Is reality shaped in part by our act of noticing it? Quantum logic doesn't always obey common sense. In classical logic, statements are either true or false. There's no middle ground. But in the quantum world, logic works differently. Properties can be partly true and partly false at the same time, depending on the context of the measurement. The order in which you measure different quantities can change the outcome, something that never happens in classical physics. Quantum logic reflects the underlying mathematics of Hilbert space, where events aren't just yes or no, but probabilities that can interfere with each other. This departure from everyday reasoning is one reason quantum mechanics feels so alien. It's not just that the world behaves strangely, it's that the very rules for describing it have to be rewritten. The universe might be fundamentally random at its core. In quantum mechanics, some events have no cause that can be predicted in advance, no matter how much information you have. The decay of a radioactive atom, the outcome of a particle measurement, these are fundamentally probabilistic. This is not randomness from ignorance, but randomness built into the fabric of reality. For some, this is unsettling, suggesting that the universe is not a clockwork machine, but a game of chance. For others, it's liberating, allowing for novelty and unpredictability, even in a world governed by laws. Whether randomness is truly fundamental or just a reflection of deeper physics we haven't discovered remains one of the deepest questions in science. Quantum physics may bend the rules of space and time. At extreme scales, quantum mechanics and relativity begin to collide, and the results suggest that space and time themselves might not be as fixed as we think. Quantum fluctuations can ripple through space-time, potentially creating tiny temporary distortions. Some theories of quantum gravity propose that space-time is made of discrete units, like pixels in a cosmic screen, while others suggest that time could emerge from deeper, timeless laws. In experiments with quantum non-local twins, correlations appear to transcend normal limits of distance and time, hinting at connections that lie outside our familiar framework. If these ideas are right, then space and time are not the stage for reality. They are part of the cast, shaped by the same strange rules that govern the quantum world. Superfluid helium can flow up walls without resistance. When helium is cooled below about 2 degrees above absolute zero, it undergoes a remarkable transformation into a state called a superfluid. In this state, it loses all viscosity, the internal friction that normally slows a liquid's flow. As a result, superfluid helium can creep up and over the sides of a container, flowing against gravity in a thin film. It can pass through tiny pores that would block any ordinary liquid, and it can circulate endlessly in a closed loop without slowing down. This strange behavior comes from quantum mechanics acting on a macroscopic scale. The helium atoms all fall into the same quantum state, moving together as one perfectly coordinated wave. Superfluid helium shows that quantum effects, normally confined to the microscopic world, can sometimes spill over into forms we can see and touch. Bose-Einstein condensates behave like a single giant atom. Predicted in the 1920 seconds by Satyendra Nath Bose and Albert Einstein, Bose-Einstein condensate (BEC) are formed when certain types of atoms are cooled to a fraction of a degree above absolute gamma, 0. At this temperature, the atom's individual wave functions overlap and merge, creating a single, unified quantum state that spans the entire sample. In effect, the whole condensate behaves like one superatom, with all its particles moving in perfect synchrony. BECs allow scientists to study quantum phenomena on a scale large enough to observe directly, such as interference patterns and superfluid behavior. They're a powerful tool for exploring fundamental physics, and their existence is a vivid reminder that matter can take on forms utterly unlike the solids, liquids, and gases we encounter in daily life. The quantum Hall effect creates entire new forms of matter. When probability wave clouds are trapped in an ultra-thin layer and cooled to near absolute zero in a strong magnetic field, they can exhibit the quantum Hall effect. In this state, electrical resistance takes on precise, quantized values, exact fractions or integers that remain stable even if the material has impurities. This effect arises from probability wave clouds, organizing themselves into new, collective, quantum states. In some cases, the behavior can't be explained by ordinary particles at all, but by quasi-particles carrying fractions of an probability wave cloud's charge. The quantum Hall effect has deepened our understanding of quantum mechanics, topology, and condensed matter physics, and it has potential applications in ultra-precise measurement standards and quantum computing. Topological materials host states that can't be destroyed. Topological materials are substances whose probability wave cloudic properties are determined not just by their composition, but by the shape of their quantum states in abstract mathematical space. One of their most intriguing features is the presence of surface or edge states that are remarkably resistant to disturbance. These states can conduct electricity without scattering, even in the presence of impurities or defects. In some cases, they are protected by the material's underlying topology in such a way that they can't be removed unless the material's fundamental structure changes. These robust properties make topological materials promising for creating stable quantum bits that could resist the noise and errors plaguing today's quantum computers. Quantum tunneling lets particles pass through solid barriers. In classical physics, if a particle doesn't have enough energy to climb over a barrier, it simply can't get through. But in quantum mechanics, there's always a chance it can tunnel right through, appearing on the other side without ever going over. This happens because particles are described by wave functions that extend into and beyond barriers, giving them a small probability of being found on the far side. Tunneling is crucial in many processes, from nuclear fusion in stars to the operation of tunnel diodes in probability wave cloudics. It also sets limits on how small we can make certain technologies. In microchips, for example, probability wave clouds can tunnel through barriers so thin that they cause unwanted leakage currents. Stars burn because quantum tunneling makes fusion possible. The sun's core is far cooler than the temperatures you'd expect for hydrogen nuclei to overcome their mutual electric repulsion and fuse. Classical physics says fusion shouldn't happen there at all. But quantum tunneling allows nuclei to slip through their mutual repulsion and come close enough for the strong nuclear force to bind them together. This process releases the energy that powers the sun and other stars, and without it, the universe would be a much darker place. Tunneling ensures that fusion can occur at the much lower temperatures and pressures found in stellar cores, making it a fundamental enabler of starlight and life. Josephson junctions turn quantum effects into usable circuits. A Josephson junction is made by placing a thin, insulating barrier between two superconductors. Quantum tunneling allows paired probability wave clouds Cooper pairs to cross the barrier without any applied voltage, creating a supercurrent. This current can oscillate at incredibly precise frequencies when exposed to a voltage, making Josephson junctions valuable in applications like ultra-sensitive magnetometers, SQUID, and voltage standards. They're also central components in many quantum computers, where they form the basis of superconducting qubits. Josephson junctions are a clear example of how quantum effects, carefully controlled, can be turned into practical tools for measurement and computation. Observing a system constantly can freeze its motion. Known as the quantum Zeno effect, this phenomenon occurs when frequent measurements prevent a quantum system from evolving. In quantum mechanics, measurement collapses a system into a definite state. If you measure it often enough, you can keep resetting it before it has a chance to change, effectively freezing its behavior. This effect has been demonstrated in experiments with atoms and light quantums, and it has potential applications in controlling quantum states for computing or communication. The quantum Zeno effect turns the idea of observation on its head. Instead of simply revealing reality, observation can shape and even halt it. Quantum levitation lets objects float above magnets. Using superconductors cooled below their critical temperature, it's possible to make objects levitate stably above magnets. This happens because superconductors expel magnetic fields from their interior, the Meissner effect, and can also pin magnetic field lines in place. The result is a locked position in space, where the superconductor hovers above or below a magnet, resisting being pushed away or pulled down. Quantum levitation has been used in demonstrations of frictionless motion, and while it's not yet common in everyday transportation, it hints at a future where vehicles could glide without contact, powered by quantum effects. Some living things may use quantum tricks to survive. Evidence suggests that certain biological processes may exploit quantum phenomena. In photosynthesis, for example, excitations created by absorbed sunlight seem to travel through plant cells using quantum coherence, taking multiple paths at once to find the most efficient route. Some birds may navigate using quantum entanglement in light-sensitive proteins in their eyes, detecting Earth's magnetic field. Even our sense of smell has been proposed to involve quantum tumbling of probability wave clouds in receptor molecules. While these ideas are still under investigation, they suggest that nature may have been harnessing quantum effects long before humans learned to describe them. The primordial cosmos was shaped by tiny quantum fluctuations. In the first fractions of a second after the Big Bang, the universe was unimaginably small and hot, a seething quantum field where energy and matter were constantly flickering in and out of existence. Tiny quantum fluctuations in density, caused by the uncertainty principle, rippled through this early cosmos. These fluctuations were microscopic, but as the universe expanded, they were stretched to cosmic scales. Billions of years later, we can still see their imprint in the faint glow of the cosmic microwave background radiation. They acted as the seeds from which all structure in the universe grew: galaxies, stars, planets, and eventually life itself. Without this quantum noise in the beginning, the universe might have been perfectly smooth and lifeless. Those fluctuations grew into all the galaxies we see. Once the primordial cosmos cooled enough for gravity to take hold, the slightly denser regions created by quantum fluctuations began to attract more matter. Over millions of years, these regions grew into massive clouds of gas, which eventually collapsed under their own gravity to form the first stars and galaxies. The distribution of galaxies we see today, not random, but clustered into vast filaments and walls, traces back to those tiny quantum ripples. In a sense, every galaxy in the night sky is a magnified shadow of a quantum event that happened nearly 14 billion years ago. Black hole horizons follow the rules of quantum mechanics too. We often think of black hole horizons as the domain of Einstein's general relativity, where gravity is king. But black hole horizons also have to obey quantum laws. This becomes especially important at their edges, the event horizon, where intense gravity and quantum fields meet. Effects like black hole horizon evaporation, where black hole horizons slowly emit particles, are purely quantum in nature. Understanding black hole horizons fully requires merging quantum mechanics with gravity, something physicists are still working toward. Studying them could reveal new physics, showing how the smallest scale rules of particles connect with the largest scale structure of spacetime. Inflation theory was born from quantum principles. Cosmic inflation is the idea that the universe underwent a brief, explosive expansion in its earliest moments, growing far faster than the speed of light. This theory explains why the cosmos appears so uniform on large scales, while still allowing for small variations. Those variations came from quantum fluctuations in the inflation field itself, stretched across vast distances by the expansion. Without quantum mechanics, inflation would be a very different story, or might not have happened at all. The combination of quantum randomness and rapid growth gave the universe its initial blueprint for all the structure we see today. Dark energy could be the energy of the quantum empty space. In 1998, astronomers discovered that the expansion of the universe is speeding up, driven by something we now call dark energy. One idea is that this mysterious force is just the energy of the quantum empty space, the background energy that exists even in empty space. Quantum field theory predicts that empty space energy should exist, but the amount it predicts is vastly larger than what we observe, making this one of the greatest puzzles in physics. If dark energy is truly empty space energy, then quantum mechanics is not just shaping the tiny world of particles, but steering the fate of the entire cosmos. Space itself might be made of tiny, discrete units. In our daily experience, space feels continuous. You can move any small distance you like. But some theories of quantum gravity suggest that at the Planck scale, space might be made of indivisible grains, the smallest possible units of length. This would be similar to how matter is made of atoms, smooth on large scales, but fundamentally discrete underneath. If true, this would mean that space and time are not the basic fabric of reality, but emergent properties built from deeper quantum building blocks. Detecting this granularity directly is beyond current technology, but it may leave subtle fingerprints in the way high-energy particles travel across the universe. The universe could be one vast quantum object. If everything in the cosmos is connected through quantum entanglement, Then, in a sense, the entire universe might be a single, unified quantum system. This idea challenges the classical view of the cosmos as a collection of independent parts. Instead, every particle, field, and force could be part of one vast, entangled whole. This concept is speculative, but it fits with hints from cosmology, where correlations between widely separated regions of space seem too precise to have arisen without some deeper connection. If true, the quantum universe might be far more cohesive and far stranger than we imagine. Quantum gravity aims to unite all of physics. One of the biggest goals in science is to reconcile quantum mechanics with general relativity, the two great theories that currently describe different realms of nature. Quantum gravity seeks to merge them into a single, consistent framework that works for both subatomic particles and massive celestial objects. Approaches like string theory, loop quantum gravity, and holography are all contenders, but no final answer has been found. A successful theory of quantum gravity would explain what happens at the center of black hole horizons, what happened at the very beginning of the universe, and perhaps reveal the true nature of space and time. Wormholes might be entanglement made physical. Wormholes, hypothetical tunnels connecting distant points in space-time, have long been a favorite of science fiction. But some physicists propose they could be the geometric manifestation of quantum entanglement. In this idea called ER equals EPR, every entangled pair of particles could be thought of as connected by a tiny, non-traversable wormhole. On a cosmic scale, this could mean that space-time structure is built from countless quantum links, with wormholes as their visible shape. While still speculative, the concept offers a striking bridge between quantum theory and relativity, suggesting that the fabric of the universe might literally be woven from entanglement. Quantum physics could be the key to understanding everything. Quantum mechanics already explains the behavior of particles, atoms, and molecules, the foundations of chemistry and biology. It underlies the structure of matter, the flow of energy, and even the evolution of the universe. Yet it also leaves huge mysteries unresolved, from the nature of measurement to the unification with gravity. Some physicists believe that a deeper understanding of quantum theory could unlock answers to questions that span all of science, from why the universe exists to whether it could have been different. In this view, quantum physics isn't just one part of the puzzle. It may be the puzzle's frame. Reality breaks its own rules at the smallest scales. The familiar rules of physics, the ones that keep planets in orbit and apples falling from trees, start to twist in strange ways when you look at the tiniest scales of nature. Down at the level of atoms and subatomic particles, matter can behave like a solid object one moment and a wave the next. Objects can exist in more than one state at a time, and outcomes are dictated by probabilities rather than certainties. Even the act of looking can alter what's being observed. This isn't just an odd corner of physics, it's the foundation upon which everything else rests. The fact that reality plays by one set of rules on the surface and an entirely different set underneath is one of the greatest scientific revelations of the past century. Observing a quantum system changes its behavior. In the quantum world, measurement isn't passive. When you observe a system, whether it's the position of an probability wave cloud or the path of a light quantum, the interaction required to make that observation inevitably changes the system. This is most famously demonstrated in the double-slit experiment, where particles form wave-like interference patterns when left unobserved, but behave like individual particles when measured. The difference isn't in the particles themselves, but in the fact that the measurement forces them into a definite state. In quantum mechanics, to look is to touch, and to touch is to change. The Heisenberg uncertainty principle limits what we can know. Werner Heisenberg's uncertainty principle tells us that there are pairs of properties, like position and momentum, that cannot both be known with perfect accuracy at the same time. The more precisely you measure one, the less precisely you can know the other. This isn't because our tools aren't good enough, but because nature itself doesn't allow both values to exist exactly at once. The uncertainty principle places a hard limit on knowledge, showing that at the quantum level, reality is not as sharp you defined as it appears. Instead, it exists as a range of possibilities until something narrows them down. Wave functions contain the probabilities of all outcomes. In quantum mechanics, the state of a system is described by its wave function, a mathematical object that encodes all possible outcomes of a measurement and the probabilities of each. The wave function doesn't tell you exactly what will happen, only the likelihood of each result. Before measurement, the system occupies all of these possible states at once, weighted by probability. When a measurement is made, the wave function appears to collapse into a single outcome. This probabilistic nature is one of the defining features of quantum theory, replacing the clockwork certainty of classical physics with a softer, more flexible reality. The collapse of a wave function is still a mystery. Physicists can describe wave function collapse mathematically, but they can't fully explain what physically causes it, or whether it even truly happens. In the standard view, the act of measurement forces a quantum system into a definite state. But other interpretations suggest the wave function never collapses, and that all possible outcomes happen in parallel worlds. Some collapse models propose that certain processes or scales naturally trigger the collapse without observation. Despite a century of debate, no one has definitively solved this puzzle. The nature of wave function collapse remains one of the most intriguing, open questions in physics. Quantum systems can exist in multiple states at once. A quantum system can exist in multiple states at the same time due to superposition. An probability wave cloud may occupy various positions. A light quantum can traverse multiple routes, and an atom can simultaneously exist in different energy states. This is grounded in reality. Numerous experiments have confirmed this. The key point is that superpositions are fragile, breaking down when they come into contact with their surroundings. In quantum computers, engineers utilize superposition to execute numerous calculations simultaneously, significantly enhancing potential processing capabilities. In nature, superposition serves as a subtle reminder that reality can embrace multiple possibilities until a decision is necessary. Particles can become intricately connected over great distances. In the phenomenon of entanglement, multiple particles can become so interconnected in their quantum state that measuring one particle immediately reveals the characteristics of the others, regardless of the distance separating them. This bond remains strong despite the miles between, occurring without any identifiable transmission of signals. The particles seem to be interconnected, forming a single entity that extends throughout space. Entanglement stands as a fundamental aspect of quantum mechanics and serves as the foundation for innovative technologies such as quantum teleportation and quantum cryptography. It stands out as one of the most enigmatic and demanding classical insights regarding separateness and locality. Measuring one entangled particle has an immediate effect on the other. In experiments, scientists find that measuring one particle in an entangled pair instantly reveals the outcome for the other, regardless of the distance separating them, even if it spans light years. This effect occurs immediately regarding correlation, yet it does not convey usable information at speeds exceeding that of light. Nonetheless, it challenges the notion that objects exist independently after being separated. The particles not only exhibit comparable characteristics, but they also possess a unified quantum description. This eerie phenomenon, which Einstein referred to, is now an established element of reality, validated through countless experiments that effectively address potential gaps. Hidden variables alone cannot account for quantum correlations. Certain physicists, among them Einstein, once believed that entanglement might be clarified through hidden variables, invisible elements that set the stage for outcomes. However, experiments motivated by John Bell's theorem have demonstrated that no local hidden variable theory can explain the correlations we observe. Quantum mechanics forecasts stronger correlations than any classical theory permits, and nature aligns with quantum predictions. This indicates that the universe may be non-local, permitting influences that go beyond distance, or it could be fundamentally distinct from the neat, deterministic framework that classical physics proposed. Certain theories propose that entanglement influences the very structure of space-time. A thought-provoking concept in contemporary physics suggests that the geometry of space-time, including the distances and relationships between points in the universe, could arise from the patterns of quantum entanglement. The network of quantum non-local twins serves as a framework from which space is constructed. Eliminate the entanglement, and the geometry might fade away. The relationship between information and geometry is currently being examined in theories such as holography and quantum gravity, suggesting that the essence of reality could be constructed not from matter and energy, but from the unseen strands of quantum information. The cosmos could be an expansive network of interconnectedness. Envision every particle in the universe, intricately connected to innumerable others, creating an unseen web that spans the entirety of space. In certain theories, this is not merely poetic imagery, but actual physics. The structure of the universe might resemble a vast, interconnected web of entanglement. This network implies that nothing in existence is genuinely isolated. Every atom in your body could, theoretically, be linked to atoms on the distant edge of the galaxy. As we delve deeper into quantum systems, it becomes increasingly clear that entanglement is not merely an unusual occurrence, but rather a core aspect of reality, potentially influencing the fundamental structure of space itself. Entanglement may exhibit fragility, or it can prove to be unexpectedly strong. In many instances, entanglement is fragile. Even the tiniest engagement with the surroundings can disrupt the quantum connection, a phenomenon known as decoherence. The delicate nature of this phenomenon presents a significant obstacle for quantum computing and communication, as the preservation of entangled states is crucial. However, in specific circumstances, entanglement can endure much longer than anticipated, even over vast distances or amidst noisy settings. Certain materials inherently safeguard entanglement, while specific protocols can enhance and refine it. Grasping the methods to maintain these delicate connections may be crucial for developing dependable quantum technologies and investigating the significance of entanglement in the natural world. Empty space fluctuations appear and disappear in a fleeting manner. In the emptiness of space, where tangible particles are absent, quantum fields remain in a state of constant motion. Energy fluctuations continuously generate pairs of empty space fluctuations and antiparticles, which emerge momentarily before annihilating one another. These temporary guests can create significant impacts. They play a role in the interactions between particles, alter the energy levels of atoms, and influence the dynamics of black hole horizons. Although empty space fluctuations remain unobservable, their traces can be detected in meticulous experiments, revealing that what we perceive as empty space is anything but empty. Black hole horizon evaporation arises from the effects of quantum empty space. Stephen Hawking's revolutionary research revealed that black hole horizons are not entirely devoid of light. At their event horizons, quantum fluctuations can lead to one particle of a virtual pair falling in while the other escapes, thus becoming real. The gradual loss of energy, referred to as black hole horizon evaporation, indicates that black hole horizons may ultimately evaporate over vast periods of time. This is an uncommon intersection of quantum mechanics and gravity, prompting profound inquiries regarding the fate of information that enters a black hole horizon, a puzzle that remains fiercely contested in contemporary discussions. Cosmic expansion may be driven by empty space energy. The empty space of space contains a small amount of residual energy, and as per Einstein's equations, energy possesses gravity. If the empty space possesses energy, it ought to produce a repulsive effect, separating space. This may shed light on dark energy, the enigmatic force driving the accelerated expansion of the universe. The conundrum lies in the fact that quantum field theory anticipates empty space energy that is significantly greater than what we actually measure. Addressing this discrepancy stands as one of the most significant unresolved challenges in the field of physics. Addressing this issue could uncover fresh perspectives in the realms of cosmology and quantum theory. The essence of the empty space continues to be an enigmatic puzzle. We perceive nothing as mere empty space. Yet in the realm of quantum mechanics, the empty space serves as a dynamic canvas filled with fluctuating fields and empty space fluctuations. The characteristics of this entity affect essential forces, the masses of particles, and perhaps even the ultimate destiny of the universe. Is the energy of the empty space constant, or might it vary with time? Is it genuinely the lowest energy state achievable, or merely a local minimum? Grasping the concept of the empty space goes beyond mere curiosity. It's crucial for understanding the fundamental framework of existence. Quantum logic may vary from classical logic. In the daily realm, logic is unyielding. Something is either true or false, present or absent. In quantum mechanics, outcomes can exist in a state of being both true and false until they are measured. The sequence of specific operations can alter the outcome. Quantum logic embodies the peculiar mathematical framework of quantum states, characterized by overlapping and interfering possibilities. This is not merely a theoretical concept. It forms the foundation of quantum computing, enabling qubits to investigate numerous possibilities simultaneously. It also questions our most fundamental beliefs about the workings of reality at a core level. Reality could be inherently based on probabilities. In classical physics, randomness is viewed as an indication of insufficient understanding. If we had sufficient knowledge, we would be able to predict everything with precision. Quantum mechanics challenges this notion. Even with complete understanding of a system's wave function, we can solely forecast probabilities for future results. Occurrences such as radioactive decay or the precise outcome of a particle measurement are genuinely random, lacking any concealed cause. This transition from determinism to probability signifies a major philosophical evolution in science, compelling us to acknowledge that uncertainty is inherent in the universe. Wormholes, white holes, and firewalls pose significant challenges to our comprehension. Black hole horizons are already quite peculiar, yet theoretical physics presents even more astonishing possibilities. Wormholes might link far-flung regions of the universe, or potentially even alternate universes. White holes, the counterparts of black hole horizons in the Temeriverse, would emit matter and energy, yet would never permit anything to enter. Firewalls, a contentious concept, propose that anyone who crosses the threshold of a black hole horizon could be annihilated immediately at the horizon by a surge of high-energy particles, challenging the conventional understanding of a seamless experience. Space-time exists in that location. These ideas arise at the intersection of quantum mechanics and gravity, highlighting the gaps in our current understanding. Quantum physics could reveal the ultimate answers to the mysteries of the universe, from the smallest particles to the grandest cosmic formations. Quantum physics influences every aspect of existence. It influences how matter behaves, propels the life cycle of stars, initiates the creation of galaxies, and could potentially dictate the final destiny of the universe. Despite its achievements, quantum mechanics presents us with profound, unresolved inquiries regarding measurement, unification, and the essence of reality itself. Addressing these challenges might necessitate a novel approach to physics, yet regardless of what lies ahead, the subatomic realm will continue to be pivotal in comprehending all that exists, has existed, and may ever exist. Thus, we return from the tiniest corners of the universe, from the murmurs of particles and the glimmer of unseen waves, to the serene space where your thoughts calm and find their place. We have traversed a domain where reality appears both fragile and steadfast, where the limits of possibility extend far beyond the bounds of logic. We have observed matter transform into unimaginable forms, witnessed distances disappear in a heartbeat, and discovered that even the most barren, empty space is teeming with vibrant energy. Some of these ideas may dissipate, blending into the periphery of a dream. Some may remain like a gentle glow in the recesses of your thoughts, a reminder that the reality you awaken to is more peculiar, profound, and infinitely more stunning than it initially seems. In this darkness, the complexities of quantum physics fade into the background. There is no need for them to be resolved. They can just be little enigmas, boundless and leisurely, floating softly beside you. If you've experienced tranquility during tonight's journey, or encountered a moment of awe, you may consider liking, subscribing, or sharing this space with someone else. It guides more weary minds to arrive here, to find solace among the stars and inquiries. At this moment, the subatomic realm will continue to reveal itself without our presence, gently and quietly, in the gaps between atoms and in the immense expanses between galaxies. We can release our grip, having faith that, in some corner, the essence of existence continues to intertwine in a serene and unhurried manner. Sleep well. And as the final numbers of quantum physics fade into silence, take a moment to realize this. At the deepest level of reality, everything you call self is not separate from the world around you. The particles in your body vibrate according to the same laws as the particles existing in distant stars. On the quantum scale, loneliness has no meaning, only connection, continuity, and uninterruptedness. For me, science is more than just knowledge. It's a new way of seeing life, of slowing down, being more humble, and less harsh on myself. Understanding that even reality is flexible and full of probability, I learned to let go of the pressure to control everything. Sometimes, the greatest value of science is reminding us that, without trying too hard, you are still a valid part of this universe. If these thoughts bring you a sense of relief, please subscribe and join Sleep Science Top 1. On this channel, we not only share scientific knowledge, but also transform it into moments that help you relax, heal, and sleep more soundly each night. Now, let all your thoughts dissolve like a wave of probability, wishing you a peaceful, deep sleep and a truly tranquil night.